Hey everyone, Mr. Fritz here. I just can't do another intro. I just don't feel like I have it in me. So I think I need to get a little bit of help. Eliana?
Hey Mom, we're first there. This year. Here I am.
About?
Dogs.
Not dogs. Logs.
Dogs.
Logarithm.
Logarithmic.
Taking the remittance up. What can you say? Logarithmic.
Logarithmic question.
Regression.
Wow, thanks Eliana. I feel a whole lot better. Now I'm ready to just dive right into this and talk about logarithmic regression. All right, so when do we use logarithmic regression? Well, we have to first talk about when do we decide between what type of regression model to use. We have linear regressions, exponential regressions, quadratic regressions. So logarithmic regressions are used to model situations where growth or decay accelerates rapidly at first and then slows over time. So the idea here is that we have an accelerated growth, something that happens really quickly. In this case, we're going up fast and then slowing down. And over here, we are going down quickly and then kind of tapering off, going down not quite as quickly. So that's what models are logarithmic regression. And again, just keeping in mind that the acceleration is in the beginning and then it slows down over time. As far as the form of the equation, you're going to see something that looks like this. Y equals a plus b times the natural log of x. So that's what you're going to use in your logarithmic regression on the calculator. Notice it's in natural log form. All the input x values, it's really important. Think about your domain for logs. They must be positive. No zeros or negative numbers in for your x's. When the b value is greater than 0, think again about what that means as far as logs. It's kind of like having an exponent that's positive over the x. Or you can also think about it as like your multiplier for your y values. And we're going to be increasing. The function's going up whenever this b value is positive. Now, if you think about multiplying those natural logs by some positive values, they're going to be getting bigger and bigger, and that's why this is actually increasing. Another way that you might think about this is y equals b times the natural log of x plus a. That might be a format you're more comfortable with. And in that case, you can think about the b value being like what gets multiplied by the y's. And so that if we're positive, we're going to continue to increase like normal. And if we're negative, we're going to actually flip and reflect over the x-axis. So let's go to the examples here and take a look at our first example that's comparing this data table. And here you see we have years and life expectancy. So this is one of those situations that you should expect to be logarithmic in its nature. So it starts off with kind of a rapid growth, and then it slows down over time. And you can see here that the life expectancy over a century has really changed quite a bit, with just a few years difference towards the later part of the data. So we're going to jump over to the calculator here and actually use this data set from 1900 all the way up to 2000 to chart this data and make a logarithmic regression about it. One thing to keep in mind is that we're not going to start at x equals 0 when we actually type in the data. And normally we would with most regression models, but remember, you can't have a 0 or non-positive x value. So let's go over to our calculator, and we're going to actually start off with x equals 1, and then we're going to go on through the end. 1, 2, 3, 4, all the way up to, I think, 12. Okay, and so now let's go over to the calculator, and if you forget how to do this, we're going to press the Stat button. We're going to click enter or hit enter on edit, and we're going to edit our lists. And so if you need to clear out an already existing list, you can just scroll up to L1, L2, press clear, and then enter, and that'll clear everything out. So we're going to type in all the x values, 1 all the way up to 12. And then we'll type in all of the y values. Make sure that you are carefully putting all of them in so as to not make any errors. Okay, and now that I have all of the data in, we're going to actually go over to the logarithmic regression. So we're going to hit Stat, go over to Calc, and we're going to calculate the logarithmic regression. That's the natural log, not the linear regression, but the natural log regression. Everything should be in order here. Your x list should be L1, your y list should be L2. And so as long as that looks okay, you can just hit that enter button a few times and take a look at your regression. Now, one thing you'll notice here, it gives me an a value and a b value, but one thing I am going to want is that r squared value that kind of checks how strong my regression is. So actually, we're going to have to go into the calculator settings to turn that on. So let's do that actually before we go further anymore. And the way that you're going to get there is if you press the second catalog, and we can scroll down. We're looking for diagnostic on, or if you're clever here, you could just click on that D button, and that's going to jump down to the D's, and we're going to scroll down to diagnostic on. Up there it is, and hit enter one more time to run the function. Now it's done that. So let's run that regression one more time. We're going to scroll down to logarithmic regression, hit enter, 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 and hit enter one more time. And there's our a value, our b value, and our r squared value. So let's go ahead and write down that equation. So here's my equation, y equals 42.5 plus 13.9 times the natural log of x. Notice that b value is positive, which should make sense as the life expectancy is going up, so that kind of fits as a quick little error check. In the next part of the example, we want to use the model to predict the average American life expectancy for the year 2030. All right, so here's our equation, and we have to be kind of clever here. Remember, we took the x values and we didn't put in 1900 and all that stuff. We changed those to 1, 2, 3, 4, and all that stuff. We're going to actually be putting in 2030 in for x, but we're going to have to actually use the x values that we use for our model. So I think we went from 1 to 12, and so 2020 would be 13, and 2030 would be 14. So basically what we're getting after here is that the x value is x equals 14. So why don't we use the same equation here, and we're going to plug in for the life expectancy. That should equal 42.5 plus 13.9 times the natural log of 14. So if we go over to our calculator and we can second quit out of the table, and we can type in 42.5 plus the natural log, 13.9 times the natural log of 14, and there's our 79.18, so we'll take that out to 79.2 is our life expectancy, rounded to 3 significant figures. So 79.2 years, let's throw some units on there. And that's it for that one. We're just plugging in a number, and we are evaluating. So the last thing we need to do here then is just check, does this regression model fit the data, or is it a good fit for the data? So in order to do that, we really have 3 questions that we need to answer to justify our answer. Number 1 is we have to take a look at the r squared value, see how strong that is. We want close to 1. We're going to check the scatter plot, make sure that that kind of looks logarithmic. And then finally, we're going to just take a look at whatever the situation is for this, this model. So in order to check out what that r squared is, let's go back over to the calculator, run our regression one more time. And that r squared is 0.956, 956. So we can write that guy down. And that's a pretty good r squared value. Again, we want it to be closer to 1. Closer to 1, the stronger it is. So that's a good r squared value to talk about the strength. As far as the scatter plot, let's go back to the calculator, and we're going to have to actually look at this data. So we're going to go to the y equals screen. We can clear out any equations that we might have had up there, turn on our plots. And if we were to graph this, we probably would not see anything because it's not fitting the data. So we're going to have to restructure our window a little bit. As far as our window goes, the data is going to go from 1 to 12, and actually let's go from 0 to 13. Give a little bit of a buffer on either side. And then for our y values, looks like we're going from about 40, and we can take it up to maybe 80 or so. And then we'll hit graph, and there's our data. So it looks like it could be linear, maybe. You could see the logarithmic shape, but I would say it's not super conclusive. We can't rule out logarithms, but I would say there is some ambiguity here. But you could make the case that it is tapering off towards the top. The increase is not as fast. So we can say that maybe it's logarithmic from the actual scatter plot. So we're going to need some more information here. And then finally, for the situation, now we just want to see, does it make sense that the acceleration of life expectancy would be so rapid in the beginning and then taper off at the end? And it really should. You're not going to be going up by life expectancy by 4 or 5 years or 6 years for a really long time. And if you continue to do that for another 100 years or so, now we're living to like 200 years old. And that's not going to be the case. So it does make sense that this would level off. And so we're going to say that it increases quickly, and then we could say the increase slows down. So that would make a good case for a logarithmic regression. So I guess to answer the question, Yes, this is a good model. So why don't you try this example here? It's very similar to what we just did. It's got 3 parts. Pause the video, give this one a shot, and see how it goes. And here are the solutions that I have for you try one. There's my equation. There is my number of games approximately. And I did say, yes, this is a good scatter plot. Again, remember to use x equals 1 as your starting value. Otherwise, you're going to have a domain problem. So hopefully this went okay. It was a good fit. And again, the video game sales should make sense to kind of taper off. It's not going to keep increasing forever.